Okay, let's unpack this. Imagine you're listening to a piece of music,
Yeah.
and it feels like the melody is just climbing and climbing, getting higher, maybe forever.
Okay.
But somehow, without you quite realizing it, you're back where you started, just different.
Ah, like Bach's canon per tonos, the endlessly rising canon.
Exactly that one. It uses these really clever modulations, right? So each time the tune repeats, it's a step higher.
But it circles back.
It circles back to the original key, yeah, but like an octave higher. And Bach himself wrote something in the margin, something like, "As the modulation rises, so may the king's glory."
Hmm. Suggesting something deeper than just a musical trick.
Right, it feels like a paradox, doesn't it? A circle that somehow still moves forward. That's what the sources call a strange loop.
And this idea, this strange loop, or sometimes tangled hierarchy,
Yeah.
it's not just, a neat trick in music or a clever Escher drawing. It turns out to be surprisingly fundamental.
Fundamental how?
Well, it pops up all over the place. In mathematics, logic, definitely art, but also biology. Even how we think about our own minds. Or artificial intelligence.
Okay, so that's what this deep dive is really about, exploring this powerful recurring pattern. We're pulling from a bunch of material that kind of weaves these threads together.
Highlighting people like Kurt Gödel, the mathematician,
M.C. Escher, the artist.
and Johann Sebastian Bach, the composer.
Yeah. And the sources suggest thinking of them as like shadows cast in different directions by some central solid essence.
That's a great image. And the material itself often uses these dialogues, right? Between characters like Achilles and the tortoise.
Oh, yeah, the crab, the anteater.
Yeah.
They use analogies and stories to make these really complex ideas feel more graspable.
So our mission here really is to guide you through these sources, pull out the key insights.
Help you get a feel for what that central essence might be, like a shortcut to understanding these connections.
And it's interesting how the sources themselves kind of mirror the ideas, using these layered dialogues, recursive structures.
To help us wrap our heads around concepts like levels and self-reference. Very meta.
It is. So where do we start? Formal systems.
Yeah, let's start there. The foundation. Formal systems. So these are systems built on really strict, predefined rules for manipulating symbols.
Right. And at first, those symbols, they're just marks on paper. They don't mean anything inherently.
The source uses a simple example, the PQ system. You've got PQ and hyphens.
And rules. Like if XPYQZ is a valid string, where XYZ are strings of hyphens, then you need Z to be the sum of X and Y hyphens. Something like that.
So like PQ, that fits the pattern. 2 hyphens, 3 hyphens, sum is 5 hyphens.
Exactly. That string, or theorem, is generated just by following the rule. No meaning needed yet.
But then meaning can come in if you find this isomorphism.
Right, an isomorphism. It's basically a mapping, a connection between the valid strings the system produces, the theorems, and true statements about something else entirely, like arithmetic.
So in that PQ example, if P means plus, Q means equals, and hyphens are numbers.
Then PQ suddenly means 2 plus 3 equals 5. The formal string maps onto a true statement about arithmetic.
And the meaning emerges from the structure.
Precisely. It's what the source calls passive meaning. The system's rules are fixed, they determine what's possible. Finding the mapping just reveals a meaning that fits. The meaning doesn't change the rules.
Which is really different from how our language works, isn't it?
Totally different. In natural language, learning a new meaning for a word can actually change how we use language, how we form sentences. The rules can evolve. Meaning is active. It shapes the system.
Okay, passive meaning in formal systems. Now, another key idea for these systems is the decision procedure.
Ah, yes, the decision procedure. Think of it as a guaranteed test.
Like a recipe or an algorithm you can just follow step by step.
Exactly. You feed it any string of symbols from the system, and it will eventually stop and tell you definitively, yes, this is a valid theorem, or no, it's not.
Finite number of steps. Guaranteed answer.
Right. For that simple PQ system, the decision procedure is easy. Just count the hyphens before P, count those between P and Q, add them up, and see if it matches the count after Q. Simple check.
But why is having such a procedure so important?
Because without one, proving something is not a theorem could be impossible. You might have to search through an infinite number of possible derivations. A decision procedure gives you a shortcut, a definite answer.
Okay, so we've got formal systems, passive meaning, decision procedures. Seems pretty neat and tidy.
But it turns out there are fundamental limits, especially when the systems get powerful enough. And that's where Kurt Gödel comes in, and things get really interesting.
Right. Gödel, he was looking at these big formal systems for number theory, systems trying to capture all mathematical truth about numbers,
And he introduced this absolutely brilliant idea, Gödel numbering.
which is like a
But-
coding system.
Exactly. A way to assign a unique number to every single symbol used in the formal mathematical language.
Yeah.
And then a unique number to every possible sequence of symbols, every statement, every formula, even every proof.
So like a unique serial number for every sentence of mathematics.
Pretty much like its own phone number or license plate. Yeah.
That's the point of doing that.
Here's the genius part. It allows statements within number theory to operate on two levels at once.
2 levels.
Yes. On one level, a statement is just talking about numbers like, 7 is prime.
This is standard stuff.
But on the second level, using the Gödel code, that same statement can be interpreted as talking about other statements of number theory, or even about itself.
Whoa. Self-reference. Built right into the math using numbers.
That's the key trick. It allows the system to talk about itself from within itself.
And Gödel used this. How? He brought in a paradox.
He did. He essentially found a way to translate the ancient liar paradox, this statement is false, into the rigorous language of number theory.
How does that work in math?
He constructed a very specific mathematical statement, let's call it G. And using his Gödel numbering, the meaning of statement G, when decoded, was effectively, this statement G cannot be proven within the formal system.
Okay, my head's starting to spin slightly. This statement cannot be proven. What happens then?
Well, think about it. If statement G could be proven within the system, then the system would be proving something that claims it's unprovable. That would make the system inconsistent, proving falsehoods.
Right, that's bad. So G can't be proven if the system is consistent.
Correct. But if G can't be proven within the system, then what it says about itself, this statement cannot be proven, is actually true.
So G is true, but unprovable within the system.
Exactly. And that was Gödel's bombshell, his incompleteness theorem.
It showed that any formal system that's consistent and strong enough to include basic arithmetic must be incomplete.
There will always be true statements about numbers, like G, that the system simply cannot prove using its own rules and axioms. The source calls them irreparable holes.
You can't just patch it, like add G as a new axiom.
You could try.
Yeah.
But Gödel showed that if you add G, or even if you add its negation, the new, bigger system still has other true but unprovable statements. It just creates a new Gödel statement for the new system.
It just keeps happening.
It keeps happening. The source says number theory multifurcates. It branches into infinitely many possible consistent versions, different brands of number theory, none of which can capture all the truths.
Wow. And there was more, wasn't there? Something about consistency?
Yes, the second incompleteness theorem, equally devastating. It showed that if a formal system, like the ones we're talking about, is actually consistent, then it cannot prove its own consistency using only its own methods.
So the system can't even vouch for itself.
Not from the inside, no. You need assumptions from outside the system to prove its consistency. It's another loop you can't close from within. You can't use the system to prove the system is reliable.
That's profound. The irony here, the strange loop, is that Gödel used this super rigorous formal proof to basically import a self-referential paradox, the very thing these systems tried to avoid, right into their core using that numbering trick.
Exactly. It revealed a fundamental inherent limit to what formal axiomatic systems can achieve. Truth is bigger than proof, in a sense.
And these ideas, paradoxes, loops, levels, they're not just stuck in math, are they? The sources show them popping up elsewhere.
Oh, absolutely. Think about other classic paradoxes, like Russell's paradox in set theory.
The set of all sets that don't contain themselves?
That's the one.
Yeah.
Does that set contain itself? If it does, it shouldn't. If it doesn't, it should. Boom. Contradiction, arising from a seemingly simple idea of sets referring to themselves.
Or in language. Grelling's paradox.
Right. The word heterological, meaning an adjective that's not described itself, is heterological. Heterological.
It ties itself in a knot again.
It does. And even basic logical reasoning has this issue. As Lewis Carroll showed with Achilles and the tortoise keeps demanding a new rule to justify using the previous rule of logic.
Leading to an infinite regress. You can't pin down the ultimate justification for logic itself using only logic.
So people tried to fix these issues, especially in logic and math, by imposing strict hierarchies. Russell's theory of types, for instance.
That's the idea of different levels: object language, meta language.
Exactly. Level 0 is basic objects. Level 1 is statements about level 0 objects. Level 2 is statements about level 1 statements, and so on. The key rule: a statement can only talk about things on lower levels. No looping back, no self-reference allowed.
Sounds neat. Does it work?
It helps avoid the formal paradoxes in set theory and logic. But applying it rigidly to everyday language seems kind of brittle.
How so?
Well, the source gives an example. In this book, I criticize the theory of types. A perfectly normal sentence, right?
Seems fine to me.
But according to a strict theory of types, it's meaningless. It refers to this book, self-reference, and it discusses the theory itself, which should be on a higher level.
So the theory bans you from even talking about it within the system it describes.
Pretty much. It's described as overkill. It throws out perfectly good, meaningful communication along with the paradoxes. Even just explaining the theories seems to violate it.
So strict hierarchies aren't quite the answer for everything, but the idea of levels and how things interact across them, maybe in a more tangled way, that seems important.
Incredibly important. And that's where Escher and Bach come back in so beautifully in the source material.
Right. We started with Bach's endlessly rising canon, that perfect musical strange loop.
And Escher, who was fascinated by Bach, made visual equivalents. His crab cannon print shows a musical theme played forwards and backwards at the same time, looping visually.
And ant fugue.
Yeah, that one explicitly shows levels. Tiny ants form the shapes of letters. The letters form words. The words repeat in patterns.
Yeah.
It's structure emerging from structure.
That layering happens in biology too, doesn't it?
Absolutely. DNA itself, you have the primary sequence of bases.
A, T, C, J.
Then the secondary structure, the double helix. And it folds further into tertiary structures. Proteins do the same thing. The linear chain folds into a complex 3D shape that determines its function.
And the source mentioned polyribosomes, like molecular cannons.
Yeah, where multiple ribosomes read the same messenger RNA strand one after another, like voices in a round or cannon, all producing the same protein. It's parallel processing on a molecular level.
There's also that connection between DNA replication and something called quine sentences.
Right. A quine is a programmer sentence that can print itself out. DNA acts like that too. It contains the instructions for building things, its use, but it also acts as a template to be copied, its mention. That distinction is crucial.
And biology still has huge mysteries related to these levels, right? Like differentiation, how does the same DNA lead to a brain cell and a liver cell?
Exactly. Or morphogenesis. How do simple rules followed by individual cells lead to the complex shape of a hand or a wing? It's all about how information and structure emerge across different scales. Very tangled hierarchies.
Which leads us, I guess, towards intelligence, both ours and artificial.
Definitely. The source really connects these ideas to how we think about thinking itself.
There was that convergence in the 20th century, logic, computation, psychology.
Right. People like Babbage, way back, with his analytical engine. He already had the idea of a store, memory, and a mill processor.
And Ada Lovelace, who worked with him, she saw it could do more than just math, maybe compose music.
And she noted its ability to change its own instructions. Babbage apparently called it eating its own tail. Another early glimpse of self-reference or loops in computation.
Though she was skeptical about machines truly originating anything new.
A debate that continues today. But in AI development, the source notes a recurring theme. Progress often came with creating higher-level programming languages.
Like LISP, languages closer to how humans think.
Exactly. Now, it's argued that these languages don't technically add more power. Anything they can do, basic machine code could theoretically do. It would just be incredibly complex.
So what's the advantage?
The advantage is perspective. The new concepts and structures in these higher-level languages suggest new ways of thinking, new approaches to problems that might be totally obscure at the machine code level. They shape how you think about the problem.
That relates to the common phrase, computers can only do what you tell them to do.
Right. And the source says, well, yes, that's true in a strict sense, but it's also misleading.
Why misleading?
Because for any complex program, you, the programmer, don't actually know all the consequences of the rules you've set up. The interactions can lead to completely unexpected emergent behaviors.
Stuff you didn't explicitly program in, but arises from the complexity.
Precisely. Which feels a bit like how human behavior can be surprising, even to ourselves sometimes.
Though computers are still very rigid compared to us, aren't they? The SHRDLU example.
Ah, yes. Winograd's SHRDLU. Amazing early AI. Understood commands about a block world. But yeah, if you misspelled a word, it would probably just crash. Humans are way more flexible with imperfect input.
This whole area touches on the big philosophical debate mechanism. Are minds just machines?
A huge question. The philosopher J.R. Lucas famously used Gödel's theorem against mechanism.
How?
He argued that humans can see the truth of the Gödel sentence from outside the system, while a machine, being equivalent to the formal system, would be trapped inside and couldn't prove it. Therefore, minds aren't machines.
Makes sense on the surface. What's the counter-argument in the sources?
The counter is that this doesn't necessarily show a fundamental difference. A sufficiently complex machine, or a human brain, might achieve self-awareness and a sense of will not through magic, but through the incredibly complex structure and organization of its physical parts, operating on many, many levels.
So our feeling of free will, our consciousness,
Yeah.
it emerges from the physical substrate.
That's the idea prevented. It's an emergent property of the system's complex, layered, maybe even tangled structure. Our brains have this structure naturally. A sufficiently advanced AI might develop an analogous emergent consciousness. The source even says, provocatively, will be mechanized.
Wow, that's a strong claim.
It is. The analogy used is the ant colony, Ant Hillary.
Right, dumb ants, smart colony.
Exactly. Individual ants are simple, following basic rules. But together, through their interactions, structured across levels, ants, teams, castes, the whole colony, they achieve complex, seemingly intelligent behavior, problem-solving, adaptation.
Intelligence emerging from the interaction of non-intelligent parts.
Yes. And the source talks about maybe active symbols in brains or colonies, complex subsystems interacting, versus the passive symbols of a formal system or text. Intelligence is this dynamic multi-level process.
Like SHRDLU again, where the parts weren't neatly separated modules, but were deeply and intricately meshed together.
A more tangled approach, yeah. Maybe that's closer to how real intelligence works, less like neat boxes, more like interwoven threads.
And what about superintelligence?
The sources touch on that. Would we even recognize it? Is it just faster thinking or fundamentally different concepts? Could it be like trying to understand Bach squared? Maybe it's already here in systems we don't recognize as intelligent in our terms. It's speculative, but tied to these ideas of levels and complexity.
So pulling these threads together, Gödel's math, Escher's art, Bach's music, biology, AI, the recurring pattern is levels, emergence, and these tangled hierarchies or strange loops.
It really seems to be a fundamental aspect of complex systems. It challenges simple, linear, rigidly layered ways of thinking about things.
And it brings us back to meaning. Is meaning just something we impose as interpreters, or can it be inherent?
That's a deep question. Is there a jukebox theory for meaning in the brain, like we have built-in hardware to decode it? Or is meaning always relative to the system, the context, the interpreter, like defining weight only relative to Earth versus using relativity?
How do we recognize the patterns in Bach or find meaning in symbols? It feels tied to our own internal structure, doesn't it?
It seems to be. Which leads back to the mind and consciousness. The source describes consciousness as an intrinsically high-level phenomenon.
High level, meaning not reducible to the lowest level.
That's the implication from Roger Sperry's view, mentioned in the material. He saw conscious awareness, ideas, thoughts, as real causal forces operating at the top level of the brain's hierarchy. They interact with each other, influence lower levels. Ideas cause other ideas.
Like software running on hardware, but the software level has its own reality and causal power.
Kind of. And framing it with Gödel is suggestive. Just like statement G is true, but unprovable at the low level of the formal system. Maybe consciousness, subjective experience, meaning. These things are easily described and understood at the high level of mental organization, but might be fundamentally unexplainable, not even in principle, if you only look at the lowest level of neurons firing or chemicals reacting.
So trying to explain consciousness purely by looking at neurons might be like trying to understand the plot of a novel by analyzing the ink molecules.
That's a good analogy for the perspective offered. Understanding ourselves requires grasping this tangled hierarchy of levels inside our minds.
How does our sense of judgment, beauty, simplicity, things that feel intuitive, almost artistic, how do they emerge from the brain's physical processes?
The sources suggest it's this emergent, high-level functioning, drawing on logic but also on something more holistic, this art of judgment that arises from the whole system.
Which brings us back, looping around again, to Gödel, Escher, Bach, the Eternal Golden Braid.
It's presented not just as a connection between fields, but as a symbol for the mind itself.
A beautiful many-voiced fugue, a tangled hierarchy where things are happening on many levels simultaneously.
And the source material itself gets playful with this, right at the end. The characters in the dialogue start wondering if they're just characters.
Achilles asking the tortoise, "Did you suspect otherwise?"
And the tortoise worrying about just reciting canned Achilles remarks.
Only for the author figure to chime in, but you have the feeling of doing it freely, don't you? So what's the harm?
A final, meta-level strange loop, questioning their own reality and free will within the constructed dialogue, echoing all the deeper questions about our own minds.
So we've taken quite a journey through these strange loops and tangled hierarchies. We've seen this pattern challenging simple views in math, art, music, biology, AI.
Right across the board, showing how complexity levels and self-reference seem fundamental.
And the core puzzle really persists.
Yeah.
How do things like meaning, intelligence, consciousness, maybe even free will emerge from these complex, rule-governed structures at lower levels?
It remains one of the deepest questions.
So thinking about all this, these tangled levels, the idea that will might emerge from physical complexity. Here's something for you, the listener, to mull over. Does your own sense of having a will, of making choices freely, feel any less real after considering these ideas? Where do you maybe notice your own strange loops or tangled ways of thinking when you reflect on yourself or the world?